Hello, welcome to our presentation on triangular clustering. I will introduce myself and my team. My name is Srivarna Jenny, PhD candidate, Kennesaw State University. Andrew Henshaw, PhD candidate from Kennesaw State University. He is also affiliated with Georgia Tech Research Institute. This research is being guided by Dr. Shireen Nee, Professor of School of Data Science and Analytics. On the right hand side, you can see the QR code which will direct you to our website and to this presentation. As an analytical and data science student, what's in our data matters a lot. So first we'll understand what the input data we are considering here and the standard clustering algorithm that we are comparing with our novel clustering algorithm, which is based on the Lugnet triangulation, and we'll also show you a demo of the working of our clustering method. The data here we are considering is from scikit-learn, which is a 2D data set with various interesting visuals. Human eyes can differentiate between the clusters, whereas the algorithm failed to do so. So here is a varied range of different types of data structure, from clearly understandable clustering methods to no structure. These data points are coordinates on xy coordinates, and they do not need any normalization. Label here is a no label because it's a supervised learning and cluster is based on visual understanding. We have compared again some of the standard clustering algorithm of SAS Enterprise Minor. We considered average, centroid, and void, and k-means. The drawback of these are they are very sensitive to the similarity matrix and between all pairs of the clusters, and the outlier and noise on the data set could affect the clusters which is formed, and they are not optimal clusters. So we were looking at the scikit-learn algorithm, affinity propagation, and spectral clustering. These may not produce the best result compared to the k-means, but because this is again a sensitivity to the similarity matrix between the data points, and they tend to have difficult to be grouped into, because they can change at any based on the starting point. They can change which cluster it belongs to. Here is bridge and mean shaft. Bridge has sensitivity to the parameters for fine tuning, and they are best for spherical shapes, whereas the other complex shape they do not do a good job in handling the clusters. Whereas mean shaft also has a problem with the parameter neighborhood parameter update, so they also form a different cluster and their sensitivity to it. One of the recent popular one is the DB scan, which is density-based spatial clustering application. This clustering method has worked on various densities, but it is computationally expensive and for a large data set because it also depends on some of the choices of the parameters used here. Now let's come to our clustering algorithm, which is the Lugnet triangulation. This is based on the named after Boris Lugnet, who worked in 1934. So triangulation is a subdivision of the area into triangles. Triangulation has a property that the circumcircle of each triangle does not contain any points of the triangulation. This maximizes the size of the smallest angle in the triangle and tends to avoid triangle with one or two extremely acute angles. So each of the possibility of triangulation that splits the quadrangle into two triangles satisfying the Lugnet condition, and the requirement that circumscribe all the triangles have empty interior. The circumcenter of Lugnet triangles are the vertices of the Voronoi diagram. So in the 2D case, the Voronoi vertices are connected via the edges that can be derived from adjacency relationship of the Lugnet triangles. If two triangles share an edge in the Lugnet triangulation, the circumcenter of them are connected in the Voronoi diagram. So let us look at the pseudocode of our algorithm. So first we do Lugnet triangulation of all points, and for each point we assess the similarity of all the associated triangles using the formula L ratio, the length of sides of triangle to the overall average of length of sides of the triangle. And we discard any highly dissimilar triangles and repeat this until we discard. So here you can see the progression or removal of mismatched triangles, and there is a video of our working of our algorithm, how it forms these triangles and discard the dissimilar triangles to form the clusters. Then the advantage of our method is that it is using a circumscribed circle. So the notion of the Lugnet triangulation extends to 2 or higher dimensions, and it's scalable for a large data set and can be generalized. So here you can see the comparison of the other algorithms, and our triangulation clustering algorithm competes against the top well-known algorithm, which is DB-scan and spectral clustering. So and we also can generalize it to any kind of data set. So we are looking at some of the complex real-world data set to compare and also do a parallelization to improve the speed. So we're working on higher dimension data and hoping to progress to get a excellent clustering algorithm. We would like to extend our special thanks to Dr. and Professor Dr. Nee for her guidance and constant encouragement and support towards this research, and also special thanks to Dr. Seema Singhari for her support. Thank you.